Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently assistant professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In module 9, we are discussing about the biogas production from biomass, particularly from the slurry biomass or wet biomass. And in previous lectures, we have discussed about overall process of the biogas production as well as the factors that affects the biogas production. So herein we'll continue with the factors affecting the anaerobic digestion as well as the sampling procedure for the biogas as well as the sampling from the digesters. So before proceeding further and going to the digester, there are few other parameters that we can discuss here. And similar to the HRT, we have solid retention time, we have organic loading rate. So those parameters we will discuss and then we will move towards different type of digesters. So to begin with, if I say the organic loading rate, so it is the amount of biomass, actual biomass which is loaded in the digester on each day. Okay, so it is minus liquid, the total slurry minus liquid, I can say, is the organic loading rate. Keeping OLR steady is very important to support the healthy microbes, because if the quantity of the biomass increases or decreases, that eventually affects the digestion capacity of the microbes. Therefore, it is very essential for effective anaerobic digestion and biogas production. Usually, it is measured as the amount of volatile solid per unit volume of the digested per day. Now, this OLR affects number of microbes, as I said, in the digester. If OLR is increased, it should be done slowly so that microbial population can adjust it. If we increase it, let's say all of a sudden, then the number of microbes are limited, whereas the amount of feed is increasing. So they may not be able to adjust immediately, and because of the overeating, it may cause dying of the microbes as well. No, because it is affecting directly the microbial digestion capacity. Therefore, it is very important for designing different kind of digester. For example, if I take the anaerobic lagoons or for plug flow and mixed flow digester, maintaining a steady rate of OLR is very important. It is also important because we have to maintain a uniform solid retention time and hydraulic retention time. And it has to be noted that hydraulic retention time and solid retention time are very different. Okay. So when we say hydraulic retention time, I have already discussed, but solid retention time is, you can say, it's a important factor that defines for how long the solid is going to stay in the digester. Okay. So it keeps the slow growing methanogens in the system to turn acetic acid, hydrogen and CO2 into biogas. If SRT drops too low, what will happen that methanogens will be lost at a faster rate, and because of that it will cause harmful volatile fatty acids to build up and potentially stick to the digester, and therefore the overall activity of the digester will get reduced. In plug flow and fully mixed digester, SRT is same as the HRT. Okay. So adding too much new waste too quickly can reduce SRT and wash the methanogens. Whereas in mixed covered lagoons, SRT is much longer than the HRT. You have to remember the SRT is solid retention time, whereas HRT is hydraulic retention time. So in plug flow and fully mixed digesters, usually HRT and SRT are similar. So we often think that they are same, but they are not same, rather they are different. Particularly when we are dealing with the covered lagoons, SRT is much longer than the HRT. So if HRT falls below the design value, the biogas production and waste treatment efficiency will decrease. Therefore, it is very important that we should also look into the SRT. So we have now OLR, which also dictates that how much volatile solid is there, and then we have SRT, and then we have HRT. These all three actually deals with the residence time of the feedstock in the digester, and they are very important because they directly affects the efficiency of the digester, anaerobic digestion, as well as the quality of the biogas. Similarly, the term that we saw, volatile solid. So, volatile solid is the portion of solid that can burn and used to estimate the organic matter in the manure. And managing volatile solid is very important. As I said, that it directly affects. So, if volatile solid is getting affected, the amount of volatile solid is getting affected, then it will affect the OLR. Therefore, it is very important to keep a stable OLR. Okay, so if we don't manage the volatile solid, managing a uniform OLR will be very challenging, as well as it will become problematic for the anaerobic digestion or biogas production. Now, it has to be noted here that the manure, because we started with the dairy farm and like animal manure and the swine, hogs, etc. So, the manure usually contains both organic volatile solid as well as the inorganic ash. Now, the organic matter includes protein, fat, and carbohydrates, which we eventually need for the biogas production, but the ash is not important. So, typically, what happens? The protein and fat breaks down quickly, while carbohydrates converts to simple sugar and degrade very fast. Cellulose and hemicellulose are relatively slower, and lignin is the most difficult and resistant to the biodegradation process. Therefore, if we maintain the volatile solid amount and we can maintain the amount of protein, fats, and cellulose and hemicellulose in a particular ratio, we will be able to get a uniform biogas yield from the digester. Similarly, toxic compound in anaerobic digestion are also very important, particularly for the if we have to decide about the feed, then it becomes very important as some many of the biomass sources have chemicals that can slow down or stop the methane production in anaerobic digester. Now these chemicals can come from the detergents, can be bleach, can be quaternary ammonium compounds, can be antibiotics, can be pharmaceuticals, can be pesticides. If such compound enters the digester when we are doing co-digestion, definitely in the manure we may not find it. So when we are doing co-digestion with the other waste like food waste processing, then what will happen that they will start killing the microbes or they will inhibit the digestion process. And therefore, to manage this risk, we have to do continuous assessment that we call anaerobic toxicity assessment. So we take the random sample of the waste and test it for anaerobic toxicity assay. That is called ATA. The operator who is operating the plant, they can evaluate the risk versus the benefit and discuss the waste sources with generator to understand the potential toxins. Besides that, there is one more important factor. As I said that the feedstock composition is very important for any kind of biogas production. So for that we have to analyze the biomethane potential. So one thing we already analyzed is how much toxicity is there. But besides that, we have to analyze the biomethane potential, how much biomethane we can extract. And for that, usually there are two methods. So this is experimental method and then we have theoretical method. I mean, then they are further classified into the pilot scale. For example, this is into BMP test, this is a spectroscopy, which is theoretical method. Here we have theoretical and then we have indirect methods. So these methods we can use to do it. In experimental method, as the name itself suggests, what we do biochemical methane potential analysis, which is BMP. So you can say one of the most widely used laboratory scale method to quantify the methane potential of organic substrate. In this, what we do batch digestibility test. The waste sample is included with an active microbial consortium consisting of anaerobic heterotrophs and methanogens. Okay, so it's same like a digester, but we can say a lab scale mini digester. So what we do, we put the sample with the inoculated consortium of microbes that has anaerobic heterotrophs and methanogens, and then we measure the biogas production over time and compare the blank control reactor that contains only inoculum. So let's say I have this a small scale thing. Initially, I will put the microbe. I will measure the biogas produced if there is any. Then on the second step, I will take again the vessel and we will put the microbes. We will put the biomass slurry, organic substrate, and we'll measure the methane release over the time. And then we'll do the methane produced here. Let's say this is Q2 and this is Q1. To know what is the exactly methane coming from this organic substrate, we have to measure Q equals to Q2 minus Q1. The reason is because if there is any methane that is coming without organic substrate, that may be because of the microbes and if there is something in the water because of that. So that should not be counted as part of this organic. So we will subtract it and then we can do the BMP test. Now here how we calculate the net biogas production. So biogas produced from the waste reactor minus biogas from the control. In addition, volatile solid reduction is also monitored to estimate the fraction of organic matter that is readily biodegradable. Okay. So besides that, MPSAs, BMPSAs are very simple. They are cost effective and reproducible, but they are conducted under idealized laboratory conditions. So what we are doing in lab, we are taking a vessel, we are putting the microbes, and then we are putting the biomass in the slurry form, and then we are under ideal conditions, ideal temperature, we are running it. While in the actual life, when the biogas plant or the anaerobic digester is installed outside, we don't have any control on the temperature and other parameters. Then there, definitely the efficiency will be different than what we do in the lab, but however, it will be more or less near. It will be similar. Okay. So you can say, although it doesn't give the accurate result, but it gives a estimate which is good enough to operate the plant on day-to-day basis. Similarly, if we are talking about the bulk production and the quantity is too large, then this overestimation may lead to problem in the overall yield calculation of the process, or you can say the biogas yield of the process. So here we have in BMP test, conventional and automatic methods. Then we have pilot scale testing. So pilot scale testing is a more realistic but resource intensive approach. So as the name itself suggests, what we do, we build a pilot scale unit, a reactor that is like kind of mini version of the full scale digester. Okay. And then we replicate the operating conditions such as temperature, loading rate, mixing, retention time, and the amount of inoculum that we are providing. These all things we replicate or mimic similar to that of the pilot scale process. Now, this method accounts for operational complexities because of substrate inhibition, mixing inefficiencies, and microbial community dynamics. This provide more accurate prediction to the field performance. Okay. Now, usually the pilot scale studies are commonly used for municipal scale or commercial scale biogas project, because there we need more realistic project. The amount of volume we are dealing, even a small error of 5% can lead huge discrepancy in the overall estimation of the biogas yield. Therefore, for large scale projects or large scale biogas plants, usually we prefer pilot scale testing method. Okay. Now, similarly, we have theoretical estimation methods where we use spectroscopy, we do the CHNS analysis, and what we do, we try to measure how much carbon is there, how much hydrogen, oxygen are there, and then based on that we calculate that how much biogas it can produce using the reaction mechanism. So we can say that theoretical estimation methods for methane potential can calculate using the stoichiometric model such as Boswell equation, which predicts the methane and carbon dioxide yields based on the theoretical composition like CHONS of the substrate. And for this, I told you already in some of the previous classes that for elemental analysis, we have elemental analyzer, CHNS analyzer, and usually we calculate the O by balance. So that is one method. Now this is very rapid and inexpensive, but the problem is that these theoretical methods assumes the full conversion of the organic matter. Okay. Therefore, they represents a higher limit of methane potential. It is not necessary that in actual plant we will be able to get the 100% conversion. But then how much maximum methane we can get? These methods can easily give us that. Okay. Similarly, we can also do indirect measurement. So indirect measurement is based on the parameters rather than the direct gas collection. For example, the parameters that include total solid, chemical oxygen demand, and volatile solids, etc., which are combined with stoichiometric calculation to approximate the methane production. Similarly, these indirect methods are also, I would rather say, the indirect method. So indirect methods are very quick and inexpensive compared to experimental assays, but then they rely on the assumption that substrate is biodegradable completely and 100% conversion can be achieved. For example, under ideal anaerobic condition, complete conversion of organic compound is about 5.6 standard cubic feet of the methane per pound of COD destroyed. But then this is not necessary that it will always happen. Okay. And also the accurate use of this relationship depends on knowing the expected COD reduction. And because of these assumptions, indirect methods are less precise than the direct experimental approaches like BMP assays or pilot scale testing. Okay. In nutshell, if I summarize the different kind of processes which are used to measure the biomethanation potential, so one is BMP assay, which is laboratory scale. Now here, as I told you earlier, what we do, we take the substrate directly into a batch digestion system with the anaerobic inoculum and we measure the biogas over the time and then we compare with a blank, okay, versus control experiment. The advantage here is that these are very simple, reproducible, and directly measures the methane potential. The VS reduction can also be monitored. Okay. But the problem here is that it also overestimates the methane potential compared to full scale digester because the small scale BMP assay tests are done under the ideal condition. Okay. Similarly, if we talk about the cost is very low to moderate and lab setup is required. While if we go for pilot scale, definitely it is at pilot scale, the cost will be very high. It is most reliable estimate for full scale performance. So what we do in pilot scale is very similar like we are doing for this BMPSA, we did it in a lab scale digester. Now we build a small scale digester, anaerobic digestion unit, which actually mimics the actual digester for which we are doing it. So it operates a small scale reactor under near full scale conditions. Okay, the advantage is that it reflects the operational realities. For example, mixing, inhibition, retention time, and because of that, we get a more realistic yield. Okay, but the problem is these are expensive and time consuming as well as requires lot of infrastructure because you have to build a pilot plant. Okay, and as I said, the cost is already high. So because you have to build a pilot plant compared to any lab unit, it will be high. Then we have the third method that we discussed is stoichiometric or theoretical method, where we use the elemental composition carbon, nitrogen, oxygen, nitrogen, and sulfur of biomass and make models like Buswell equation to calculate the potential. Now CHNS, if you have done CHNS analysis, it's very rapid. So it is very rapid and inexpensive, requires only substrate composition. Okay. Of course, there is a cost involved in doing elemental analysis, but then once you know the elemental analysis, you can calculate it easily. Rest other things may not be required like a pilot plant or like BMP as a test. Okay. But the problem here is that it assumes the complete conversion. Okay. Because we are not talking about conversion. Now we are talking about how much carbon is there, how much hydrogen is there, and how much can It can become as per the reaction mechanism, how much of it can convert to the methane, how much of it can convert to the CO2, etc. And it also ignores the operational losses. Okay, but it provides the maximum theoretical possible methane yield. Okay, and that sometime we may call it overestimate, because in actual life that is not going to happen, or that doesn't happen usually. Maybe in future when we have very good microbes that can convert all kind of biomass including lignin and everything, then that may happen. But as of now there are limitations, and because of that it gives a overestimate. Okay, then there are indirect methods like that estimate using the total solid, COD, volatile solid, and other factors. Okay, these are also very quick, low cost requirement, or it cost very minimal to analyze it. So that's a major advantage. But the problem here is that it also assumes the biodegradability of all kind of biomass. Okay, and then that become a problem. Okay, the cost is moderate, but it is less precise than BMP or the pilot scale reactor or the pilot scale test method. Now coming here to the point that what are the tests that we should do? Okay. So by this we got the biogas potential, but whether my biogas plant is working fine or not, how will I come to know? And also, what is the quality of my biogas? When should I take the sample of biogas? Does my digester producing biogas constantly at the same flow rate of same quality? These are some of the questions which often you will encounter when you will go to the biogas industry. So here is a checklist. If you can see, for each feedstock, you have to test the total solid, you have to test the volatile solid. pH may not be necessary because it's biomass. You have to test the biochemical methane potential. You have to test the chemical oxygen demand. You have to test the ammonia. You have to test the TKN. You have to test the NPK, secondary nutrients, metals, microbial inhibitors, sodium, pathogens, and toxicity. Okay. Now then this biomass is now charged to the digester. Then you will have digester influent which is going in. Then you have to test the same thing. You have to test the total solid, volatile solid. You have to also test the temperature, because in the digester what is the temperature is very important. Then you have biochemical methane potential, you have COD, you have ammonia, you have TKN, NPK, secondary nutrients, metals you may not need, microbial inhibitors, and then pathogens and toxicity. But in the digester effluent, you don't need to test like what are the secondary nutrients, what is the NPK, because that will again likely to get carried away with the liquid water that we'll discuss later on. But we have digester effluent. Herein we also test total solid, that gives us that how much solid has converted, total volatile solid as well, so whether the all VS has been converted to biogas or not. The pH, because it is very important to have neutral pH before any use. Temperature, by that we will come to know if there are any variations in the digester. Volatile fatty acid, chemical oxygen demand, and then microbial inhibitors as well as pathogens. Okay. Now because it is going out, it's a digester effluent, we don't need to measure the toxicity. And similarly, we have the separated liquid. So for liquid, what we need to know is the biological oxygen demand. As I said earlier, that we can use it for irrigation purpose, we can use it as a biofertilizer. So if we have to use it as a biofertilizer, we have to know what is the NPK amount in that, what are the secondary nutrients, what are the metals present in that, and what is the sodium present there, right? These things we have to know. So this is a kind of test that you will have to do every day in a typical biogas plant or a typical anaerobic digestion plant. Okay. Now the question here is how to do the sampling. So for conventional low solid digester, both influent and effluent must be sampled. and for that you have to take the samples downstream of the feed pump while it is operating. If a storage tank with mixing and equalization exists, then sample has to be taken from the feed line that represents the combined feedstock. If multiple feedstocks are added separately, then the sample should be collected after each addition and create a composite sample proportion to their volume. Similarly, effluent sample should be collected while the flow is ongoing. Particularly in wet digester, the effluent is sufficiently mixed to provide a representative sample. Okay, the sample effluent before any solid separation occurs shall also be taken. And before collecting, allow the sample port to run for some time so that it will flush the residual material from the valves and the pipes. It's not like just you open the valve and collect the sample. Just allow it for some time to remove whatever is left over from the previous process. And once it is removed, then you take a sample. And always use a clean, appropriate container for sorting each of the samples, which is very important. So this was for low solid waste digester. Let's say if we have high solid waste digester, we have to begin with large sample. So we can select a representative portion based on the observed ratios, and then or we can divide the sample into components and way to determine relative percentage. Now this process is very complex and uncommon in farm scale digesters. Similarly, for biogas sampling, minimum 3 points. So one is exiting the digester, then after water separation, then after H2S removal. So that we get after the digester, we'll get the methane plus CO2 plus water vapor plus H2S. But once water is separated, we'll get methane, or I can say biogas plus CO2 plus H2S. Once H2S is removed, then we'll get the CH4 and CO2 only. Ideally, automated or handheld sampling devices should be used for the ease of sampling or for the sake of convenience. Okay. For off-site lab analysis, the containers which are recommended by the different testing labs shall only be used, because for every gas there is different requirement and different type of storage is done. So herein also you should use ideally the lab recommended containers. Then we have liquid sampling after the solid separation. So for that, as it is liquid, we can collect the liquid sample just after the separation. And for gravity waste separators, we can draw the sample from the liquid discharge point or a sample port given in the gravity line. It is very important to maintain the sample integrity, especially if we can do on-site analysis. It is very good if, because we are analyzing it immediately. If it remains for a long time, then some reaction may happen or some microbe will start eating whatever is present in the liquid. So that will again not give you accurate result. However, if immediate analysis is not possible, refrigerate the sample until testing so that no further reaction will happen. For off-site lab analysis, you can cool the sample immediately and transport on an ice to minimize the degradation, because you can't take the refrigerator everywhere. Okay. Now here there are a lot of other tests that can be done. So the point is, how do we remember that how many tests has to be done and how it has to be done? So for that there is a simple thumb rule that you prepare a checklist for each. For example, for low solid waste, you sample influent and effluent. So you can tick mark. The sample from the downstream of feed pump while running, you can tick mark. If there is mixed storage tank exist, feed line sample, tick mark. If there are mixture of feed, then for each feed stock, you have to take the individual sample and prepare a volume weighted composite, so you can tick mark. Then the effluent should be collected during the flow before the solid separation, so you can again make a tick mark here. Also you have to check whether you have flushed the sample port briefly or not, so you can brief, and then use clean and suitable container. So I mean, when you make a checklist, it becomes easier, and then it minimizes the chances of any human error or any kind of other error. Okay, so that you can see. Similarly, for high solid waste, we can also make a checklist. For example, here we can start with a large sample, visually select the representative portion. Then optionally, if you want, you can weigh the components to determine the relative percentage, but this is not necessary. So you can either tick mark yes or no. Okay. Now this is rarely applied in the farm scale digester. So then we have the biogas. Biogas, I said, it should be sampled at three places: digester outlet, tick mark; after water separation, tick mark; after H2S removal, tick mark. If you are using a CO2 removal system, also CO2, you can say after CO2 removal. So you can make a checkbox here and you can make a tick mark. And it is always advised that use automated or handheld devices. And any off-site analysis, then use lab recommended containers. You can make a tick mark. Okay. So this is a sampling checklist that you can do. Similarly, we can do for the liquid post solid separation. We can collect the during separation. Then for gravity separators, we can take the sample from discharge point or the gravity line port. But all these samples have to be handled very carefully. Particularly if it is on-site analysis, analyze immediately or refrigerate it. But if it is off-site, you have to cool it immediately and transport on ice, or maybe if you have a freezer or you have some setup that can keep the sample cooled and prevent the further reaction, then you can use that kind of. Now I think in many of the developed nations there are trucks, refrigerated trucks. You can use that kind of trucks where you can send the sample, so that can help. Okay. Now this is all for the parameters that affect the anaerobic digestion process, the type of parameter we need to measure or analyze, and the sampling procedure. This is all for today's class. See you in the next class. Thank you.